Suppose there is a rubber tube attached to the ceiling. This is a rubber tube and the upper end of the rubber tube is attached to the ceiling, and at the lower end we place a hook like this and pull this downwards. A force is applied to elongate this rubber tube. Naturally, the rubber tube will be elongated and the length of the rubber tube will be increased. So this is an example when a force is applied to deform a body, its shape or its size changes. Suppose we are applying a force on this body, this scale, and this is the natural shape of the body. When a force is applied, the natural shape changes. When force is withdrawn, this shape regains its original shape. So, a physical body regains its original shape or size when the deforming force is withdrawn. So this is the inherent property of this physical body. This is the scale, and regaining its own shape is its original property, inherent property. Similarly, the property of this rubber tube is also like this. When this force is withdrawn, the size of the rubber tube becomes same. This increment of the length is due to this deforming force. So as soon as this deforming force disappears, this elongated rubber tube regains its original size. And the regaining of original size or original shape of any physical body is inherent property of that body. So we can say the ability of a body, the ability of a body to regain its original shape or size when the deforming force disappears. Is known as elasticity. So what is elasticity? Elasticity is the inherent property of a physical body, and due to this property, the body regains its original shape and size when the deforming force disappears. Okay. So this is the definition of elasticity. Now, there are so many kinds of bodies, and the dependence of deforming force, the effect of deforming force is different for different bodies. Suppose if we take a rubber tube, it will be elongated to some extent. If we take another tube of material, suppose a rod, iron rod is taken, and rod is under action of an elongating force, the rod will be elongated, but the elongation will be comparatively small. So the elongation or change in shape and size is different for different bodies. Depending upon that property, we will define two things. Number one, perfectly elastic body, perfectly elastic body. So which is perfect elastic body? Suppose we have taken a rubber tube of length 1 meter. Okay. And this is attached to the ceiling, and there is another hook here, and this hook is made to apply a force. Suppose you are pulling from here to elongate this. Suppose the original length is 1 meter and you are pulling this downwards. Now you are applying a force, and when the force is withdrawn, it will regain its original shape and size. And let us assume when force is withdrawn, it regains its original shape. That means shape and size both are original. Its length becomes just 1 meter. So when a body is under action of the deforming force, and after withdrawal of the deforming force, if it completely regains its original shape and size. If the body completely regains its original shape and size, then that body is said to be perfectly elastic body. So you may define perfect elastic body in such a way: the body which regains its original shape and size completely. After withdrawal of deforming force, is known as perfectly elastic body. Okay. Now, there is another kind of body, that is perfectly plastic body. So perfectly elastic body, remember the spelling, perfectly elastic body. Now perfectly plastic body. So which is perfectly plastic body? Perfectly plastic body a body which retains its default size and shape after withdrawal of force of deformation. Is known as perfectly plastic body. Suppose you have a lump of something, anything material. It may be clay or another thing. Now you are applying a deforming force. So suppose the original shape was perfectly spherical of this lump. This are perfectly spherical, and a deforming force is applied on this body. After application of deforming force, it will be deformed like this. Somehow this portion will be like this, and after withdrawal of this force, it will retain its deformed size or shape. So this body is said to be perfectly plastic body. Actually, there is no perfect body. Actually, there is no perfectly plastic body or perfectly elastic body. We have just defined two types of bodies, perfectly elastic body and perfectly plastic body. Now, we are going to the mathematical section of this chapter. At first, we define stress. So, what is stress? Suppose the first example. This is the ceiling of your room, and from ceiling you have attached a rubber tube like this. Okay. The area of cross section of the rubber tube is equal to A, and the force applied to elongate it by you. You are applying force on this body to elongate the rubber tube, and the force applied by U is equal to F. So when F force is applied on this body, according to Newton's third law, an equal but oppositely directed force will develop within the body. So this force is force applied by external agent. You are external agent. And same but opposite directed force, same. That means if the magnitude of this force is equal to F, the magnitude of this force also will be F, but it will be directed upwards. Same force of same magnitude, but oppositely directed force will be developed within the body. So this is the force developed within the body. Why this force develops within the body? Actually, this force tends to resist the effect of this force. So this force developed by within the body is equal to F. Okay. This force divided by area, force by area, F by A, is known as stress. So it can be defined like in a way like this. Stress can be defined as the reaction force per unit area of the body. Reaction force which develops due to external deforming force. So this external deforming force is the cause. The force developed within the body is the effect. This effect is due to elastic property of this body, and stress is defined as this force, reaction force per unit area. That means force by area. That is stress. So we can say the unit of stress, force by area. So unit of stress, dyne per centimeter square in CGS unit, and it is Newton per meter square in SI unit. So this is primarily about stress. Okay. Stress can be defined as the reaction force per unit area of the body which develops due to the external deforming force. Without presence of external deforming force, stress cannot develop. So stress is the outcome of external deforming force. Now we will define strain. The same example, I will draw the same picture again. So this is the ceiling and this is the rubber tube. The original length is equal to L, and when this force is applied, the length increases. That means the rubber tube is being elongated, and the elongation, that means the change in length, this is called elongation. Elongation is equal to delta L. Actually, this sign may seem new to you. It's a Greek letter, and when we want to denote very small change of some physical quantity, very small change of any physical quantity. To denote small change of any physical quantity, we use delta. So delta L means change of length. Okay. Now, in this particular case, this strain is defined as strain is defined as delta L by L. That means change in length by original length. This is a particular case. In general, change of any physical quantity per unit. Change of any physical quantity, it may be size, it may be shape, it may be volume, it may be length. So this is known as strain. And as strain is ratio of same physical quantities, it is known unit. Strain is unit quantity. Strain is unitless quantity. Now, you may define strain in such a way. Okay. Definition of strain. Strain is defined as the ratio of the change in size or shape. The ratio of change in size or shape to the original size or shape of the body. To the original size or shape of the body. So we have defined two physical quantities, those are new to you. One is stress, another is strain. According to Hooke's law, Hooke's law, H-O-O-K-E, Hooke's law. So what is Hooke's law? Within elastic limit, this stress developed in a body is proportional to strain produced. Within elastic limit, the stress developed in a body is proportional to the strain produced in it. Now, I may ask a question to you. Between stress and strain, there are two physical quantities. One is stress, another is strain. Between these two physical quantities, which is fundamental? Now, I am writing the question. You have to answer it independently. And let me know your response through net. Which is more fundamental? Stress or strain? Explain. Now, the mathematical form of Hooke's law. So, from Hooke's law, we know stress is proportional to strain. And according to Hooke, stress by strain must be constant quantity. If stress is proportional to strain, stress is proportional to strain. So, stress by strain is a constant quantity. When we consider the case of elongation or the case of contraction, that means for an event of elongation, this is an elongation, case of elongation or contraction, you may take your eraser, your rubber eraser is like this, and from two opposite ends you are pressing this like this. Suppose this is the eraser and this is the eraser and we are trying to compress this. Now when such an event occurs, the original length, if the length is L, some length, it will compress to some extent. So this is compression. After withdrawal of the deforming force, it will regain its original shape. Similarly, after withdrawal of deforming force, it will also regain its original shape. But this is elongation, this is compression. So when the case is elongation or compression, this constant is known as Young's modulus. So in case of compressional strain or elongational strain, compressional strain or elongational strain, this constant is known as Young's modulus. Y-O-U-N-G, Young's modulus. M-O-D-U-L-U-S. Young's modulus is equal to elongational strain by elongational strain. It is also stress by strain. Stress by strain. So, it is denoted by Y. It is denoted by stress is equal to F by A. It is denoted by delta L by L. So this is equal to FL by A delta L. FL by A delta L. Now, this is the mathematical form of Young's modulus. Let us suppose there is a tube, the same tube attached to the ceiling. The original length of the tube is equal to capital L, and there is a hook like this, and from this hook a load is attached. A load is here, M, a mass is attached here to produce an elongation. So when M mass is attached here, the force due to this mass is equal to mg. Mg is equal to weight, and you know the weight always acts downwards. Okay. So the force developed within the body to prevent elongation, that F is equal to mg. Remember, this is the force due to elasticity. And if the area of cross section is equal to A, then the stress is equal to mg by A. So in place of F, we can say this is equal to mg, and this is L. Now, if the radius of this, suppose this is perfectly circular, this is a circle. So, if the radius of the circle is R, then area of cross section is equal to pi r square. So, area is equal to pi r square. Now, if you have any difficulty to understand delta L, then we can say the change in length is equal to delta L is equal to, suppose delta L is equal to small l. So this is equal to small l. So in some books, the expression for y is like this: y is equal to mgl by pi r square l. Hence, this is the first lesson of elasticity. Only you have understood to deduction, the deduction of y is equal to mg by pi r square l. Only 3 classes or 4 classes are necessary for this chapter. Try to follow the next class, and within 3 or 4 classes I shall try to cover the entire syllabus of class 9. Okay, thank you for your watch.